Okay, so I'm going to describe how to convert your CCD images that you took at our observatory into final colorized standard image files. It's the first of 3 processes that you'll use to complete our image lab here at Cabrillo College in Astro 8. So when you click on your first raw image after you've opened up CCDOPS, then you should see a box like this. This box will show up. It has some information in it, but frankly it's not very useful information. The one thing we really used to like to get off of this was the chip temperature. However, in the later versions of Windows, somehow the chip temperature always comes out as 0, which is wrong. So there's really not anything of use on here. You've already recorded at the time you were at the telescope the date and time and the other things that were going to be of value for you when you fill out your image labels. So anyway, once you see this little box, then just hit the enter key on your computer and then your image will show up. However, it'll show up too big. So what you do is over here on the left there is a magnification box and you want it to say 1 to 2 and then click apply, and then the image will shrink in half and then you can see the whole thing. So your first goal with this raw image is to correct the thermal noise. So we call that a dark frame subtraction. So your 5-minute image was building up electrons in each of the pixels, but those electrons were not just from the photons arriving from the sky and from your object, but also just random thermal noise from the jostling around of the silicon atoms in each and all of the pixels. Some of those pixels will also be so-called hot pixels. They'll be saturated, or in any event they'll be much brighter than they're supposed to be, and they're not giving fair readings of what came from the sky. You'll be able to notice these because they won't be blurred out into many pixels like actual stars are. It will literally be a single little hot point. That is not a dim little tiny star. That is a hot pixel, something you want to get rid of. And also, not all the pixels are identically sensitive to incoming light, and so they don't build up counts at the same rate from one to the other. So we can correct for these, and that's the goal of the dark frame. So what I've done is at times when we're not busy taking images, I'll be taking dark frames. I usually do 3 dark frames, and I combine these together. These images are stored on SBIG, our computer at the observatory that connects to the CCD camera, our ST2000XCM CCD camera from Santa Barbara Instrument Group. And in order to do the dark subtraction, you need to know the chip temperature because it's actually quite sensitive to the chip temperature. If you cool the chip by an additional 5 degrees centigrade, you actually cut the thermal noise, not by just a little, but you cut it in half. So it's actually important to know what temperature we controlled the chip at. So remember when we started up our image that I set the chip temperature and then we were locating your object while the cooling system was cooling our chip down to the temperature we wanted. So again, I took 3 dark frames per chip temperature. This was not with you, but when I had the time. So why did I take 3? Well, sometimes you get cosmic rays that come in, and the cosmic rays are high-speed particles moving at almost the speed of light. They hit the upper atmosphere and they cause secondary particles to be generated, and many of those make it all the way to the ground. And they're so powerful they'll go right through the dome, and they'll come down and they'll go right through and hit your chip. And you'll know because they're going to knock loose a whole ton of electrons, and so you'll get hot pixels just from that. Those are temporary hot pixels, unlike perhaps permanent hot pixels that also need to be corrected for. the hot pixels that come from cosmic rays are not going to be correctable by the dark frame, not if they're on your actual image. The best you can do there is to try and use in Photoshop the clone stamp and grab some dark sky and paste it over the top of those remaining hot pixels. But cosmic ray events here at sea level are not all that common. But sometimes they happen, and what you don't want is to have hot pixels from cosmic rays that are on your dark frames, because those dark frames are reused over and over by lots of students over many weeks or months. And so if those are bad, then they're going to spoil a lot of different images. So anyway, I take 3 of them, and when you median combine images, what you're really doing is you're taking the middle in terms of intensity of the 3 versions of that pixel. And so if one image and only one image has that particular pixel going hot because of a cosmic ray event, then it won't be counted. It'll just be dismissed because you're only taking the middle. It's different than an average. An average would not be good in this case. You definitely want to do a median. But anyway, I did all that for you, so you guys don't need to worry about that. But you might notice if I send you at some point the entire dark folder of dark frames that you'll see A's, B's, and C's. So for example, here's my naming convention for dark frames. DK5 minus 23A, that means it's a dark frame. It's 5 minutes long. It was taken at minus 23 degrees centigrade chip temperature, and it was the first one, A. And then I'll do a B and a C, and I'll median combine the A, B, and C to give a final, and that will be labeled like this, and now there's no A, B, or C involved. It's just DK5 minus 23. That's the ones that you're going to use. So if somehow you end up with a folder showing all the A's, B's, and C's, you don't want to use the A's, B's, and C's. You want to use the one that doesn't have A, B, and C for your proper temperature. Okay, so now we're ready to actually do our dark frame subtraction. So stare at your image, and I want you to especially stare at the hot pixels. So those are the little teeny single, actually this is so tiny it's hard to see, but there's one right there, right above the red dot. You see that single hot pixel? It's definitely one single pixel, not like these stars here, which spread out over maybe 100 pixels, or a dozen at least, even for the faint stars. They're really a single pixel. So those are the ones that we should correct for, and I want you to be staring at those when you're doing the actual dark subtraction. So why do we watch? Well, the reason we watch is because it's important for you to know what the dark subtraction is supposed to do, and then make sure that indeed it does it. If you don't, you could end up having to start all over again. If you just kind of mindlessly click on things and don't know what it's supposed to look like, you could end up at the end and then say, whoa, my image is gone, what happened? I've had that happen in my classes, and then there's nothing you can do except start all over from the very beginning. So it's kind of a bummer. So you want to make sure at each step that it does what you think it should do. So when you do the dark subtract, what you should see is the hot pixels will disappear, almost all of them. The sky should get smoother and less grainy. And those are kind of the two main things. It'll also get darker, so you'll notice your image will get darker. We'll show that in a later slide here. So going back, if you click on, as we showed, dark utility, dark subtract, then you pick your dark frame. So here I got DK5 minus 20. You click on it and it'll show up in this little box. This little box down here. And then you click open and it'll actually perform the dark subtract. There's one more thing to do. You have to click standard or adaptive. Now all of our frames, all of our images are done at 5 minutes. But if they were at different lengths, then the adaptive would actually scale to try and correct for the differing exposure, because the dark counts on your pixels definitely go up, roughly in a linear way with longer exposures. So it's important that you make sure your dark frame is the same length of time as your actual image. But since we do 5 minutes for everything, you can do standard or adaptive. It shouldn't make any difference. So after you click standard or adaptive, your image will at first look too dark, and that's because it has not auto scaled the let's say the curves, the levels across your image. So the way you fix that is in the little box you actually click auto and apply, and then your image should brighten back up to normal. And then we want you to make sure now that there's a lot fewer hot pixels, and the sky surrounding your object and in between your stars should look smoother and less grainy. If instead it looks worse, then maybe you did something wrong. You should at that point stop. Go backwards, try and figure out what went wrong. So maybe you used the wrong chip temperature. If so, I mean, maybe you guessed and you didn't write down the right temperature when you're at the telescope. Then you could ask me for a different dark frame. If you have the whole folder, then you can just try and choose a different dark frame. Definitely choose a dark frame that gives you the results that you should have, which is most of the hot pixels should disappear and your sky should look a lot less grainy. Also, what can go wrong is once you apply the dark frame, you don't want to apply it again. If you apply it again, then you've dark subtracted twice, and that'll definitely mess up your image. You need to apply it once and once only. If you need to back up, then in CCDOPS along the top bar there, you'll see a button for edit, and then under that a little menu, and you click undo, and it'll go backwards one step. Okay, so if everything looks good, in other words the hot pixels more or less disappeared and the sky looks smoother, then you're now ready to do the flat field correction. So that's the second correction necessary. And you click Utility, Flat Field. But first of all, before you do that, let me explain what the flat field does. So a flat field is an image of a perfectly uniform field, a perfectly uniform thing that you're going to photograph. You need to photograph it through the same telescope, with the same optics, same focus, same everything. And I usually use the twilight sky to do that. So if you wait till just a little after sunset, but definitely nowhere near time to see stars come out with your naked eye, so a bright twilight but not too bright, then the sky near the zenith is pretty much uniform. I mean, it's like virtually exactly uniform, and that's exactly what we want. I try and do these so that I'm exposing for less than a tenth of a second. Tenth of a second is not enough time to have stars begin to show up on your chip, at least as long as you don't have any really bright stars in there. I actually pay attention to where the Milky Way is at the time I do these. Even though I can't see it, I kind of know where it is. And I aim the telescope off to a place where I know there's little chance of a bright star showing up. And then again, I take several of these and I combine them together to do a single flat field, and then that is the flat field that we use for all our images for that semester. Now, if you're doing professional astronomy and you're at a big observatory, well, you're going to want to do flat fields the night of your big all-night observing run, and so that's what you do before it gets dark. But for us, this is plenty good enough. Okay, so the actual flat field image won't look perfectly uniform, and I actually don't have an image of the flat field in this presentation. I suppose I could have put it in, but it basically looks like bright gray, but it's more circularly symmetric rather than rectangularly symmetric. the actual flat field, when you look at it, will not be perfectly uniform because of several effects. So one is there's residual differing pixel sensitivities. So pixels, again, build up light at slightly different rates. Also, and this is more important, the non-uniform illumination of the square chip. So we have a round telescope aperture, obviously, and we also have a secondary mirror in the optics, and both of those are going to mean a non-uniform illumination of a square chip. Because you have a square chip and a round telescope, then the illumination is different in such a way that the corners are darker. So when you look at your image, you're going to notice that the corners, the sky where the corners is going to look darker than the sky near the center of the image. And that's an artifact of the fact that you haven't done a flat field correction yet. And then there's one other thing, and there is dust that can fall on the window above the hermetically sealed chip chamber, and sometimes that dust is not very easy to get off. Maybe the dust that came on there was a little sticky, maybe it was a piece of pollen or something, and it's better to just let that get taken out digitally than to try and actually remove the dust. So those of you in recent Astro 8s know that we do have a big dust mote that sits on our window, and it makes a big fat dust donut on all of our images. But it's okay because we remove those with the flat field. So again, what you're going to want to do is stare at your image at the time that you actually perform the flat field. And the reason is because you want to make sure the flat field does what you expect. So if you look at the image here, which is before it's been flat field, you'll notice that this corner is dark, and this corner is kind of dark, and this corner is dark, and this corner is dark, and that's the giveaway that you haven't done the flat field yet. In fact, when I grade your images, that's one of the things I'm going to look at and make sure that you actually did your flat field. If the corners are dark, that's a good giveaway that you didn't do your flat field. You might even do the flat field twice, thinking, gee, did I do it or did I not? Maybe I better make sure and do it again. Well, that's a bad thing, because then you're going to do it twice, and the giveaway for that is now your corners are going to be extra bright. So what you want is the corners to be neutral. They're going to start out dark. You correct once, and they'll go neutral. If you correct twice, they'll get bright at the corners, and if you correct 3 times, they're going to be even brighter, etc. So what the flat field correction actually does is you take the image and it will divide, not subtract, but it will divide by the flat field. So what does that do? That means every single of the 2 million pixels on this chip, the intensity is described by a number, and you're going to take that number, the computer will take that number, and it'll divide by the number in the flat field for that very same pixel. So that way, since the numbers at the corners in the flat field are going to be small, you're going to divide what's clearly a smaller number in your real image by a smaller number in the flat field image, and those two are going to cancel each other out because they're on opposite sides of the division sign, and that's the way you actually fix things. Okay, so you're going to click on the flat field. In this case, for this particular image in our PowerPoint, it's a flat that I took on September 22nd, 2015, flat field number 4. So you click on it, and it'll show up in this box, and then you click Open, and Open is what actually performs the flat field. So at that moment, then you're going to notice that the corners will now look neutral, and your sky should definitely look better. It should look more velvety, because it'll fix the residual differences in the rate at which the pixels register light. So there's our flat field image, flat fielded and dark subtracted. So now it's fully corrected. Notice that the dark corners are neutral, so that all looks good. That's what you want to make sure of. Corners look good, and the hot pixels are mostly gone. You know, if you really had like all the time in the world, then you'd take flat fields all the time. You know, I work too hard. I don't have that much time. Of course, you also need perfect weather. You need a perfectly clean sky. How often do we get that? In coastal Aptos, Santa Cruz. So there might be a few hot pixels still left, but that's okay. We can fix those in Photoshop later. Okay, so now we're ready to convert this black and white image. I know you've all been disappointed. Oh, my image, you know, I wanted a big, beautiful color image. Why is it black and white, Rick? The reason it's black and white is because so far all we've registered is the intensity in each pixel. But each of these pixels also has a filter over it. CCD cameras have well, at least the ones that we've bought, the ST2000 and the ST4K, these have filter masks. Every single pixel has its own color mask. Kind of amazing. Every time I think about it, I'm amazed. How do they make a filter that's only like, you know, 9 microns across? Anyway, somehow they do it. It's an engineering challenge, but they do it. And what you've got then is the 2 megapixels are divided into sets of 4 in a little 2x2 array. And opposite corners are green, and then the left top and bottom right corner pixels have a red and a blue over it. So you got 2 greens, a red, and a blue over each 2x2 set of pixels. And when you combine those together, that is a vector space for the color space. It's a basis vector for the color space, and it will allow you to then get the true color. Red, green, blue is kind of typical and standard and common for defining a color space. So we're going to convert these to color. So the way that'll work. It's all done in the software. Now you might say, well, but this is a pattern of 4. You need all 4 pixels just to render one color. So that means I've really only got like 500,000 different color possibilities. Yeah, the color resolution is only half of the full pixel resolution, but in fact, it's not at all noticeable. And also what we do in the software is we interpolate between pixels. So it really isn't that it will look blocky in terms of color, which is what you might worry about. The color resolution is still the full resolution, but it's only because it's interpolated. You won't notice it. You'll trust me. Trust me. Okay, so you click, and now a little box over here is going to show up. And what you want to make sure is that all these sliders here are in the middle. They should all default to being in the middle. If somehow they're not in the middle, maybe you messed around with them before and it just remembered and took that as the new default. No, you want to put all these in the middle. I really want to stress that. We do not do any color adjusting inside CCDOPS. Any color adjusting we do that in Photoshop later. The goal of taking a good astronomical image is to be faithful to the colors. So if you want to produce some kind of a psychedelic thing, that's all fine, but you're not going to do it yet. You can do that later in Photoshop and keep that one for yourself. Meanwhile, you're going to give me what is a good and faithful and properly cleaned up astronomical image. Okay, so all these are lined up in the center. And then for method, you're going to want sRGB with gamma. So that's stretched red, green, blue with gamma. So we definitely have an RGB image. We saw that a little earlier. S means it's stretched. So we stretch the color space to accommodate. And then gamma is another kind of stretching. And so what we're kind of trying to do is to optimize the dynamic range in tone and in color both. And you'll find that nearly all the images that we take, images of galaxies, of nebulae, open star clusters, planetary nebulae, things like that. Those will all definitely look best if we use sRGB with gamma. So that's what I want you to use. Sometimes, you know, I have seen globular clusters look a little better resolved in the center if you use a different method called DDP, but I'm not going to talk about that here. I'm not sure it's really legal. The colors don't look right, but at least the stellar resolution's a little better. Anyway, for your purposes, this is what we want. Then you click Process right there. And voila, we have a color image. So in this case, it's a comet. Comets usually look green. If your comet looks some weird color, then you might want to call me over, you know, if we're doing this in the classroom. If we're doing this during the coronavirus and we're doing this remotely, then, I don't know, you can email me. Tell me, Rick, my comet came out purple. Well, then we'll have to figure out what went wrong. You might have messed up your color balance. It should look green. Or if it's a comet that's missing carbon, it might just look kind of gray. I have seen that too. It's really neat when comets look green. It's due to a diatomic carbon emission line. Now you can also see the tail of the comet. And comets often have two tails. One tail will be bluish green and the other one will be gray, or yellowish rather. And this one looks kind of yellowish. This is a very faint dust tail. I don't really see another tail. Maybe off in this direction, very subtle and hardly there at all. That one would be the gas tail, and the gas tail should glow with the emission lines. So that should be some intense color like green or blue. Okay, so you are done with that image. So now we're ready to save it. So you click File, Save As, and put in your name. It should actually, for most purposes for my class, you can just leave the name alone. You don't have to change it because now you see what it's going to do is it's going to save it not as a .st2k file, but as a TIFF file as it defaults. There's a whole bunch of different formats you can use here. There's JPEGs and bitmaps and, you know, a bunch of them. But I'm going to suggest you go with TIFF because it's a lossless image file format, and that allows us to not lose anything off your image. At the very, very end, before you print it and send it to me for our gallery, then you will want to turn it into a JPEG, but don't do that yet. So just leave it as a TIFF file, and then you click Save, and you're done with that particular image. Now, in our class, we typically will let you do at least 3 images, and if it's a really difficult faint image, maybe 4, and we have time, you may do 4 or even 5 or 6 sometimes, 5-minute images, so that's a lot of images. And you have to do this step, all the steps that I just showed you, you have to do that for each and every image. Do it to completion so that you have a TIFF file for each image. One to completion, then the second to completion, etc. Once you've done all of them to completion, then we're ready to do the next step. Now, why do we do 5-minute images? And if it's a faint image, why don't we just let you take one single, I don't know, 25-minute or 20-minute exposure? There's actually several reasons. The educational reason is because I want to teach you how to stack images. That's a whole separate thing. Stacking images is a valuable little skill. But it's also good because it better preserves the dynamic range, meaning the range from dark to oversaturated pure white. If you took one single long exposure, then the bright parts might saturate, and after they're saturated, then you cannot get any levels of gray back out of them. But if instead it's a little undersaturated, that's okay. We can stretch it and work with that in Photoshop. But once it's saturated, you're done. You can't pull it ever back. So we want to keep our exposures relatively short. 5 minutes works pretty well for what we do. But there's another reason, and that is, we got airplanes and we got more and more satellites crossing, and it's possible you might have one of those cross your image. I see it usually at least on 1 or 2 images for each class every semester. Usually those aren't so easy to correct for. So if you get one of those across your image, typically if we're right there at the telescope and we notice it, then I'll let you get another image. But suppose you're taking one single image and then an airplane crosses in the last 20 seconds. Well, your entire image is now gone. You've got to start totally over. At worst, you're only going to lose 5 minutes at a time if satellite or airplane crosses. And you wouldn't want to lose any more than that, because then you start getting upset, and we don't want to see you upset. Okay, so we're done with the first stage. The next stage is to combine the images. That'll be a separate PowerPoint and a separate YouTube. For PCs, I like to use Registax. I understand Registax very well. If you have a Mac, there's other software you can use called Keith's Image Stacker. There might even be other software I don't know about. Actually, I'm going to check on that, and I may get back to you guys privately if there's better software than that. But I know a good friend of mine who's an excellent, outstanding astrophotographer, and he's always been using Keith's Image Stacker, and that's also free software. Registax is free, and Keith's is also free. All right, well, that's it for this stage. So good luck with getting your images done.